All right, so before we get started with the problem, I just want to show you that you should be drawing a diagram like you see here, especially, considering that this is the first problem like this you've solved. It will really help you to keep things straight. You'll also notice that I created a table over here. We'll be filling in our variables as we discover those. So let's look at what I did. This is the expected path of the rocket. It's a parabola shape, as you can see. I've labeled it as best I can at this point. I've got my change in X, all right? It's gonna be my range of the rocket, how far it flies. I also have my max height that I've done here. And you can see, by the way, I also have my angle. My launch angle is 60 degrees, and this is my measured velocity, the velocity that we measured in class, either outside or in the lab. You can see that I've drawn a triangle right next to that as well to help me keep this straight, because again, we're going to be using these trig functions here of sine and cosine to figure out the velocity in the x direction and the velocity in the y direction. Just a reminder, this is a vector. This right here is the measured velocity. This is what we expect the rocket to do, how fast it's going to go. But as you can see, obviously, it's traveling at an angle. So that means that part of the velocity is moving in this direction and part is moving in that direction. And so we have to split those apart. Don't forget that motion in the x direction and the y direction are independent of one another. So I've got my triangle, I've labeled my theta, my angle. I've got the opposite side, which is always opposite the angle. I've got the adjacent side, which is next to the angle, and I've got my hypotenuse right here. And again, the magnitude of this hypotenuse is going to be my measured velocity of 29 meters per second, and my angle is going to be 60 degrees. Don't forget we have this mnemonic, SOHCAHTOA, to help us remember the relationship between the trig function and the sides of the triangle. And so for sine, we know sine is equal to the opposite over hypotenuse, right? Sine, opposite over hypotenuse. And cosine is equal to the adjacent over the hypotenuse. Now, because we have the angle and we have the hypotenuse, we can rearrange this to figure out the other variable, all right? So in this case, the initial velocity in the y direction is equal to the sine of the angle times the hypotenuse. So it'll be sine 60 times 29 meters per second. And similarly, the initial velocity in the x direction is going to be the cosine of theta, the cosine of 60 times the hypotenuse. So cosine 60 times 29 meters per second. And that'll give us the velocity, initial velocity in the x direction. All right, so as I said, I worked those out over here. The initial velocity in the x direction is cosine 60 times 29, or 14.5 meters per second. And I've entered that into my table on the right. You may recall we were speaking about how there is no acceleration in the x direction. So therefore, if there is no acceleration, then the velocity is constant. And so the final velocity in the x direction is also going to be 14.5 meters per second. Now in the y direction, there is acceleration, and you might remember that the acceleration in the y direction is going to be that of gravity, and so the acceleration of gravity is negative 9.81 meters per second squared. Sorry, I ran out of room there a little bit. So we cannot just assume that the initial velocity is the same as the final velocity in the y direction. Using this trig function here, we've got that the sine of 60 times 29 is equal to the velocity initial in the y direction. And we're going to say that is 25.1 meters per second. Now, what we're going to do with this problem is we're going to set the final velocity in the y direction at 0 meters per second. And what that's going to give us is the max height of the object, because while it is true that the final velocity in the y direction would be 0 once it hits the ground, of course we know that. But what we're going to do instead, we're going to just set this as our final spot. This is going to be the change in y right here. Before we go any farther, I just filled in a few more things that we can say. First of all, and we just said that there's no acceleration in the x direction, so the acceleration would be 0 meters per second. And I've established this point right here as my starting position in the x and my starting position in the y direction. So both of those are going to be 0 meters. The first thing we're going to do, we're going to solve for time in the y direction. And again, that's going to be because we're setting our final velocity in the y direction at 0 up here. So this is going to be how much time it takes the rocket to get from its initial position of y to its final. And that, by the way, is going to be 1/2 of the total time in the x direction. We'll come back to that in a second. But for right now, let's see how we set this up. We're going to use this equation of the final velocity is equal to the initial velocity plus acceleration times time. And I'll provide you with that equation when you go to do this. We want to solve for time. So to isolate time, I'm subtracting the initial velocity and I'm dividing by acceleration. And that moves both of those over to the other side. And so I'm left with the final velocity minus the initial velocity over acceleration is equal to time. So what's our final velocity? In the y direction, it is 0 meters per second. And our initial velocity in the y direction was 25.1 meters per second. And the acceleration that we're dealing with is the acceleration due to gravity. So that's going to be negative 9.81 meters per second squared. And that will equal time, and time is in seconds. So let's check our units to make sure that we're on the right track. Meters cancel, and we have 2 seconds down here, a second squared, so that cancels with that. We're left with seconds, so that means that we're on the right track. And if you calculate that out, you're going to come up with, I'm rounding here to 2.56 seconds. And so that's our time in the y direction. So I'm going to take and fill that in on my chart over here, 2.56 seconds. Okay, now in class we did talk about symmetry a little bit, and we sort of demonstrated this with a ball. I think it was a marker. I tossed the marker up in the air and then caught it. And we said, how does the time up compare to the time down? Well, the time that it takes to go up is the same as the time that it takes to come down. So if we're measuring this as half of the time, right? It's only gone up, it hasn't come down yet. Then we can double that value, double the time in the y direction to get the time in the x direction. And I've done that. So the total flight of the rocket will be 5.12 seconds. We have the time in the y direction. Let's go ahead and solve for the displacement in the y direction, or the max height of our rocket. And to do that, we're going to use the equation of velocity is equal to distance divided by time. We want to solve for distance, so to do that, I multiplied both sides by time to isolate distance. And you'll see here that it says initial velocity plus final velocity divided by 2. Well, that's average velocity. And the reason why I've written it like that is because this equation that we're dealing with here, in fact, uses average velocity. And we use this in our first speed test that we did. You timed how long it took an object to move a known distance, and we said that was its average speed at that point. And so that's great. So what we need to do is make sure that we are using the average speed of our rocket. Well, how can we do that? Well, we know that the initial speed in the y direction, initial velocity, is 25.1 meters per second. And we're saying its final velocity is 0 meters per second at its high point. So I'm going to add 25.1 and 0 and divide by 2, and then multiply that by the time. Again, that's the time in the y direction. So the average velocity of the rocket will be 12.55 meters per second. And we'll multiply that by our 2.56 seconds, and we'll find that the change in displacement in the y direction is 32.1 meters. So its max height is going to be 32.1 meters. Okay, so the last step in this problem is going to be to figure out the range of the rocket, the displacement or the change in x, how far does the rocket fly? And to do that, I'm going to use the same equation. Velocity is equal to distance divided by time, which I've rearranged again as I just did by multiplying both sides by time. And I'm going to say that the distance is equal to the average velocity times the time. Now, first of all, notice the time. Last time we used this time in the y direction, and we can do that because we're basically establishing this high point as the end of the y direction. And we said that time is symmetrical. The time it takes an object to fly up is the same time it takes for it to fly down, because the acceleration of gravity is constant. It's always acting on that object. It's always accelerating that object down. So we need to make sure we use the right time, the time in the x direction, the total flight, in 5.12 seconds. We just said that this is the average velocity that we're talking about here. Well, you might see here again that there is no acceleration in the x direction. So therefore, the initial velocity and the final velocity are the same. So if you add those together and divide by 2, you're going to get 14.5 meters per second. So the distance in the x direction, its displacement, or the range of the rocket, is going to be, again, the 14.5 meters per second times the 5.12 seconds, or 74.2 meters. Okay, so just to recap, we measured the velocity of our rocket being fired. We tested it several times and took an average of those speeds. They were in miles per hour. We had to then convert those to meters per second. We then fired that rocket, hypothetically here, at a given angle. In this case, it's 60 degrees. And we wanted to try to figure out how high the rocket was going to fly and how far. So to do that, we first had to break that velocity of 29 meters per second into its component parts. So its velocity initial in the x direction and its velocity initial in the y direction. We then solved for time in the y direction, and then we figured out how high the rocket would fly. After that, we then calculated the range. And we've decided that this particular rocket is going to fly 74.2 meters. Now, if we take it outside and put a target out there at 74.2 meters and fire the rocket, we are never going to hit it. And the reason why is because this process completely neglects air resistance. It essentially assumes that there is no air resistance. It's sort of like an ideal situation. So what we're going to do, we're going to use this information that we've gathered, as well as a calculator online that will very easily and quickly calculate the impact of air resistance and set our target appropriately. So we're going to have like our predicted value in an ideal situation. Then we're going to have our predicted value in more of a real world sort of application. And then we'll fire the rocket and see who can hit the target and who can get the closest to the target if nobody hits it.